Welcome. My name is Dana Groff. I am a program manager with the concurrency runtime in the parallel computing platform group in Microsoft's developer division. Today we are going to talk about the concurrency runtime on UMS, Windows UMS. Now, the Windows UMS part is really going to be talked about in depth by Pedro, who will be talking after me in, I think, that room, one way, right next to us. So I do recommend that you stick around, plan on sticking around for 2 hours. You'll hear about how to program easily UMS threads here, and you'll hear about how they work from Pedro right afterwards. This is a C++ talk. If you were expecting managed code, this is a really good time to maybe go down to the P-Link talk that Igor is giving right now. He's in 515A. I will not take offense. Use your time wisely. This is a C++ talk. We are going to actually be working more in concepts. I'm going to want you to understand, take it easy. The P-Link talk is that way. I want you to understand how the concurrency runtime achieves its goals. The major pieces that make up the concurrency runtime and how you might be able to tweak them and use them. How many people here were at Rick's talk earlier this week? Okay. Now, Rick Malloy talked about the PPL and the agents library. If you did not see that talk, please watch it online on video. So that's the really good idea part. I will make certain assumptions that you understand why we're here. I'm not going to go in and tell you, hey, the free lunch is over and go into why we need to do multi-threaded code. You already know that. I am going to do a brief overview, and we're going to go into ConcRT's innards quickly. So it'll start light, and then it'll get quicker. So for those of you drinking your coffee, I'm giving you a couple of minutes, OK? Oops. Why are we doing this? ConcRT really is giving you three things. It's giving you a platform that is an abstraction on the operating system. And this platform allows you to write code that you can run on XP all the way through Windows Server R2, 2008 R2, without having to change your code. You don't have to recompile. It will run on all of those. But if you're running on XP, it's probably 32-bit, and you want a 64-bit image on Windows Server 2008 R2. What you saw earlier this week with PPL and agents allows you to provide. Let me restate that. Well, what PPL and agents allow you to do is to focus on your problem, focus on your algorithms, and focus on how to express concurrency in those algorithms naturally, without having to worry about the plumbing, without having to worry about expressing, this is a thread pool, I have to wait for these events, I have to synchronize on all these things, and I have to write all that code just perfectly, and if I get one thing wrong, it doesn't work, and I can't find that. This gives you a simpler programming model. And through that, you can express fine-grained concurrency in your application. And that will give you better performance. In the end, parallelism is not easy. You still have to think about your algorithms. You still have to make algorithms that scale. What I'm giving you is better tools that are easier to use, that are more expressive because they're an abstraction. We do that through the parallel patterns library. We do that through the asynchronous agents library. We give you some data structures that are concurrency safe is the way I use them instead of being saying specifically thread safe, because that's a very technical term, and I don't know that we are 100% thread safe, because there's things that you don't want to do sometimes. And so they are naturally concurrency safe, and I would encourage you to look at those. Because we are part of the C runtime, all your source code is there. So today, install beta 2. You can sit there and, break in your debugging code, and you can take a look at that. So it's all available to you there. And I do encourage you, when you're debugging things and you're trying to understand how things are going, you can go and look into that code. Today, we are going to talk, oh, yes, let me go on that. What we have here is also an architecture that can be built on. And that's really a lot of what I'm going to talk about today. We have these task schedulers. Again, they're kind of like thread pools. We'll talk about that in detail. And we have a resource manager. And the resource manager is an abstraction on the hardware, over the threads and the UMS threads, that allows vendors like Microsoft, like Intel, to write libraries that compose together. Last year, Intel said that they were going to be porting their thread building blocks and OpenMP on top of the concurrency runtime. They're plugging into us at the resource manager layer. And what that allows them to do is to compose across their libraries, as well as your applications that you might write with ConcRT's PPL. We also are working closely with Intel's development groups to provide one set of concepts to think about. And if you look at TBB today, they are actually shipping PPL.H, because we worked together to come up with one set of concepts for writing parallel code. They also have some great plugins to help you out, and you can probably see that down on the floor. I'm going to talk about the task scheduler, the resource manager, and UMS threads in this talk. Before we go into the details, I want to show you it working. So that's why we have this big beast here. I don't know if you can hear it. It's not doing much right now. Big fingers. There we go. Not doing anything. I would say probably 2 months, maybe 3 months ago, internally, our team contacted us in ConcRT and said, hey, we're doing some great stuff with images. And it's not scaling. Do you got something that could help us? These guys are working what you see here. Does anybody here know what a phase 1 camera is? A couple of you do. So phase 1 is the high-end digital cameras. So I don't know about you, I shoot with digital cameras. Do you guys shoot with digital cameras? My digital camera's like, what, 6 megapixels for my point and shoot, and maybe 8 for my SLR. And I keep lusting after the 15 megapixel cameras. These are 60 megapixels. This is the medium format, for those of you who remember film. Yeah, it was kind of old, but yeah. The old 4x5 film and the old Hasselblad backs. Well, Hasselblad's still around, and they put phase 1 backs. They shoot 60 megapixels. These are massive files. And they are raw files that take a long time to process, and of course, then enhance. So what you're seeing here are a series of phase 1 images. And I actually have Kenneth from that team here to tell us what is going on. So why don't you take it off, Kenneth? Turn his mic on.
Thank you, Dana. Yeah, so this is an image we built to process raw images. Raw images that come straight from the camera and that needs to be processed into a fully color-managed RGB file. So as Dana said, this is 60 megapixel images. When they're processed, they're about 384 megs, so these are gigantic files. And to process a raw image, you have to take it through various steps. So the first thing you do is you create the Bayer, you optimize the Bayer pattern, you demosaic, you remove chroma noise, you remove luma noise. In total, there's about 12 filters processing the image before you get the final beautiful RGB image. And we can, as Dana's going to show you, this scales linearly. So you can process about 2.5 of these images on this little machine back here. So I should say thanks to Phase 1 for lending us these images. They were shot by a photographer called Kaiser Bjornborg, so thanks to them.
Okay, so what I'm going to do is put it into throughput mode. And we have some little debugging things here, actually, to allow us to scale it to, let's say, 8 cores. So you can see it's going to take a little bit for the pipelines to empty out. What it does at 8 cores. Now, how many people here develop on a single core machine? Wow, nobody. How many have 2 cores? 4 cores? The 4 cores were more than the 2 cores, by the way, there. 8 cores? Good number of you. How many of you got 16? Well, OK. Robin doesn't count from AMD. This is running on an AMD 48-core machine. And wonderful machine. And we're going to actually show, right now it's running at about 30 megapixels a second. So we're going to double that. And to even stabilize it more, I'm going to turn off the pretty pictures. It's now running about 60 megapixels a second. That's easy math. You can handle that. Let's double that. Almost. Not quite. 110 megapixels a second. But let's give it the full bar. 48 cores, running between 145 and 150 megapixels a second. Pretty near linear scaling. What do you think? What do you think? And you can hear it, right? And we can see it. 99% efficiency, it's using all 48 cores. Now for this demo, I can tell you the biggest challenge was the video part. Getting that to not interfere. But these guys are awesome. Kenneth, what did you use in ConcRT to make this happen?
So first, we spent about a day introducing ConcRT, and we used agents, which work really well if we were parallelizing just one image. But we wanted to keep all the cores busy all the time, so we said, well, let's feed it like 5 different images. So we found out that agents didn't quite match the pattern that we needed for that, so we introduced the Parallel 4, which is in the Parallels pattern library. And by combining these two, we were able to achieve the linear scale, and it literally took 2 days, where half of the 2 days, half of the 1 day was installing Visual Studio 2010. So it's extremely easy to use, and it also scales better than the custom threading that we did with the Win32 threading that we did, which started to fall apart at about 20 cores. So it was very easy, and also the debugging tools that came along with that were the new Parallel Performance Analyzer was just amazing to use. It's really a game-changing library along with the debugging tool, so you should look forward to working with that.
Thank you, Kenneth. That's great. So let's give him a hand, guys. Literally 2 weeks ago, they showed me a mock-up of this demo. Not even a mock-up, a preliminary version of this demo. So this came together at the last minute, and I want to say it's a wonderful, wonderful example of what you can do with ConcRT. When you think about your problem, you need, and you've got, at this point, a serial code, or you're thinking serially, right? How many of you think in parallel? OK, so one half hands, right? We think serially. And what we have to do is start saying, well, of that, what are those unique tasks? What are those pieces of work that I want to run together that must run in serial? And I keep making my problems smaller and smaller. I decompose them into chunks that we call tasks. Don't get wrapped up in the name. groups, we then group these tasks together. Which ones are related? Which ones are working on the same data? Which ones are dependent on each other? And then we need to schedule those on the existing hardware that it's running on. Now that's your job to say, these things should be scheduled together, and this is the quality of service that I need. That's what you need to do. What the runtime needs to do is to cooperatively handle blocking events and dependencies that you've already explicitly stated in your code. It needs to make sure that when you said these things work together, that they stay together on that NUMA node or that socket. And it should manage the CPU resources so that you're not oversubscribing to those resources and forcing the operating system to start choosing between which thread should be running, instead of you choosing in your application which thread should be running. That's what the runtime does for you, and you don't have to write any code. I say don't get hung up on a task. Get hung up on figuring it out how your algorithms decompose. A task could be a lambda. If you don't like that syntax and you prefer pointers to functions, that's fine too. You can do that. If you like functors, that's great. Don't worry about it. It's just a conceptual unit of work. We have two types under the covers. And so when you are in the debugger and you're looking at it and you say, what's this lightweight task? And should I be using lightweight tasks instead of task handles? Don't worry. They're both lightweight. Lightweight tasks are used by agents. They are kind of fire and forget. They're very much like traditional threads. You start it up and it ends sometime. And if you need to know, you better write something to actually figure it out that it ended. You can schedule lightweight tasks together. And we talked a little bit about that yesterday. We had a small group down on the server floor. You can specify with which schedule groups agents and their messages should be affinitized to. Tasks, you see when you say parallel 4. And you can have a much kind of, I want to say, a fairly rich way of controlling that definition of tasks and the grouping of those tasks and how I wait or I cancel those tasks that are grouped together, right? So this is now one more conceptual piece, which is these are tasks that I wait for or I cancel together. Cooperative blocking is probably the single most important thing that we're bringing to the table here. You can do a lot of things with threads today, but what you have to do when you sit there and take a lock is you need to go into the kernel. With cooperative blocking, I run my task, and when it's blocked, that notification is given to the runtime. And so it says, it's blocked. I can use this core for another task, and I will run that other task until it's completed or until it blocks. When the first task, we count from 0 here. From the first task is unblocked, it can then be rescheduled on the same core. So what did I just do? I kept affinity. How does the operating system do it? It might do it. Might do it pretty well. Might not. It depends. Now, we are going to do a best effort to keep it on the same core. But if there are other cores available and they're not being used, it's better to go use those cores than to affinitize. And this is something that if you were writing your own code, it would be kind of hard to do. You would be saying, OK, I'm just going to make sure it stays on this. I'm going to affinitize these threads together. And they are stuck there. You don't have any way, short of writing a concurrency runtime, of saying, oh, wait, there's another core that's free. And this is the beauty of being able to rely on an abstraction and let the runtime do its work. So let's take a look at cooperative blocking. Now, this is a very simple set of code. And I don't, And some of you, if you've seen me talk before, you may have seen this. What we're going to do here is that we're going to run 3 times a small loop. And what that loop does is it creates 8 tasks and it queues them up. Writes out a message, it waits for an event, and then it writes out that it received that message. We have 2 different types of events. We have events that are provided by ConcRT, and we have Windows events, which is simply a wrapper around create event and wait for single object. So this allows me to do syntactic sugar, you might say, and be able to write fairly quick code. What you see here is that I'm going to run it as if it was running on 2 cores. So I state in my scheduler, and we'll go in this more depth later, that it's a minimum of 2 cores, and I'm just going to run on regular threads. I'm going to then do it again using a ConcRT event. So the first time is with a Windows event. Then I'm going to, first time I run it with a Windows event. The next time I run it with a ConcRT event. So let's take a look at that. So here we're at the scheduler. And let's take a look at that. So what did you just see? This is a running regular Windows blocking events, right? Pretending I'm on a 2-core machine, which I often am. So I run my first 2 tasks, and then they block. They wait. You don't get to use the other resources right now. And you have to wait until that event is set. And then the other tasks run. Now, this is just printing a message. But what happens if it was computing some significant value of pi, for instance? That would be a long time for each of those first events. And you know, if my event's going to take a long time, wouldn't it be nice to get that work done? So now I'm setting my scheduler to be able to use UMS. And I'm going to switch back to my presentation, and then we'll start off and see that in a minute. Cooperative blocking is provided to you by having things like the event class, which the concurrency runtime knows about. These communicate with the runtime saying, I'm blocked. We do that through things like the receive. When I want to receive a message, and wait to receive a message in the agents library, I'm waiting in the task group. We have simple locks like the critical section and the reader-writer lock. They're just great building blocks. Some more primitives and the context environment for block, unblock, and yielding. And you also have the ability to say, look, I really, really want to oversubscribe because I'm on XP, let's say, and I know I'm doing a Windows blocking event, so I'm going to force another thread to be handed into this environment. Those are the things that you can do with ConcRT. But let's improve that. Let's improve that without you having to think about oversubscribing. On Win 7 x64 and Windows Server R2, user mode scheduled threads are available. And when I say that, what I'm saying is these are threads that when you have a kernel blocking event, you have communication with the concurrency runtime. So now all blocking events, at least kernel blocking events and concurrency runtime blocking events, spin, waits, don't count, they are part of that kind of grand scheme of allowing the runtime, allowing the application to define what gets run while you have quantum. Because what happens when you have a kernel blocking event? You probably lose your quantum, right? You're going to go in a critical section, you're probably going to spin first, then you're going to go into kernel, and then you're going to block. That going into kernel was 3,000 cycles. So you probably now have enough cycles that you may be getting close to losing that quantum. And if you don't lose that quantum, you wait for a while, and then you get it back, and then you lose it, right? So this is a way to keep that core warm. This is a way to say, look, I know it's blocked, and it's in the kernel, and that's OK. You think, oh, well, we have this, right? It's fibers, right? Everybody here programs in fibers, right? Yeah, right. You just don't call Win32 calls, right? You can't do that. This supports Win32. It looks just like a regular thread. In fact, you can listen to it at this talk, and you can listen to Pedro talking about it, and then you should go, I'm going to just treat it like a regular thread. And that's what you should be doing, right? You just need to write your code and work with your application and let us deal with the complexity under the covers. Don't pay attention to the wizard behind the curtain, right? This is what it looks like, and I'm not going to talk to this picture because Pedro's going to talk to this picture, and his pictures are prettier. At least they move. Actually, this is one of his. The basics behind UMS is that there are two pieces to your thread. There's a kernel mode component, and there's a user mode component, which we call a user mode context. That user mode context gets controlled by the concurrency runtime. The kernel mode is handled by the kernel and the UMS facilities there. And it communicates with the runtime to say, hey, this is blocked. And oh, this is unblocked, and now reschedule it. And what we do in concert when we reschedule these things is we try to retain affinity. We are going to try to reschedule that event, that task, that context on the same core, or at least the same NUMA node. Again, our algorithm is we want to keep as local as we can. So core, NUMA node, whatever's available. That's the way we work today. So let's go back to our demo. And we see that I'm now saying use UMS threads. And then we do the exact same thing that we did in the first one. We just call the Windows event. So what do you think it's going to look like? Okay. It looks just like a concert event. So now you're running more efficiently. Internally, when we run our tests, the 64-bit platforms, Win7 and 2008 R2, give us the best performance. Now, I'm going to be straight with you guys and say, when I say the best performance, it's not 10 times. It's not 2 times. It's 8%, a small percentage point. Because we've written code that doesn't really show the beauty of this, because really it's really efficient. And it doesn't have a lot of blocking events and things along those lines. And if you start seeing a lot of speed up on UMS, that means you probably had a lot of slowdown without UMS. And you do probably need to look at your algorithms at that point. But what UMS allows you to do sometimes is to be sloppy. Okay? And that's something that you can also say about cooperative blocking, because now you don't have to worry about interdependencies on those tasks blocking each other. I could have something block on task 1 that is going to be released by task 5. And we'll actually take a look at that. Inside, we have a scheduler, schedule group, task group, structured task group. Those last 3 I like to call groups. We have schedulers and we have groups. Which one you use of those 3 really is dependent on what you're doing. Schedule groups for those lightweight tasks. That's what you use. Structured task groups are really designed for things like writing parallel for loops. These are going to be really local, structured parallelism. You don't use them with multiple threads. I mean, they may create multiple threads under the covers, but you're not going to use that task group across multiple threads, where a task group you can do that with. So the task group is heavier weight than the structured task group. So from a performance perspective, and you need to keep that equation in your mind. But it might be worth creating only one task group, which I get to reuse, and I get to use on multiple threads. That's your design choices that you get to make. And we provide these tools to make those design choices. Schedulers are the things that run the tasks. They provide work stealing queues, and you can define multiple ones. And we'll talk about that. Let's first talk about those groups. For each scheduler instance on a core, there's two queues that we really pay attention to. There's multiple queues, but there's two that you might want to think about. One is what's queued up to run, what's capable of being run right now, and a local queue. Now here I have three different groups: a blue group, a green group, and an orange group. Kind of like when you were in elementary school and they had you wear different shirts, right? OK. Consider that I actually ran a batch of these groups. One of my tasks was blocked. So I stuck it off the side. And then I continued running. Now a later task unblocks this first task. So that later task is probably working on the same data as that first task. And so what this second queue, this local queue, is, it's a reverse order queue. So that we then run it first before any other tasks that are queued up to run. So that we try to keep affinity for the cache. Again, small, subtle little things, but that's what burns you in parallelism. How many people here have actually tuned parallel code or highly concurrent code? A couple. Oh, more than a couple. How many people thought it was really a lot of fun and easy to do? Right. It's those little things that kill you. Oh, I made my structure 2 bytes bigger, and my performance goes down 20%. What? I just broke cache, right? So trying to keep things in the cache as long as possible is what makes you scale. Now, what happened there? Let's go back a little bit. I have an empty core. Before, it was running blue tasks. So what are the tasks that's going to go after? Does it go after the orange queue, which is deeper, or does it go after the tasks that were in the same group that it was just running? It goes after the tasks that are in the same group that it's running. So again, our algorithm here is to go look internally to this particular core, and when we're done, reach outside to the last group that we were running. And only if that's empty do we go to another group. Work stealing. I'm going to show you that in pictures in a minute, but work stealing queues are fairly straightforward. What happens when you sit there and you run a batch of tasks? How many people here in their threads, do all your threads run at the exact same length of time? They don't, do they? Right? So your tasks run at different lengths of time. When a task is done and the core is idle, you're not getting your money's worth from that CPU. You're just burning up time. So the schedulers look for empty work and reschedule that work on the idle resources. That's work stealing. So we look at that quickly. Go back to the 48-way monster here. Everybody's seen the ray tracer. There's a ray tracer running serially. We're getting about 12 frames per second. We're not running on all 48 cores. We're only running on one node here. I run it in parallel 57 times. By the way, we're only using 6 of the cores because we're using one node socket. And if you look at this picture, you see they're not evenly distributed. If you were writing OpenMP, this would be evenly distributed on a static partitioning. And that is because shadows take a lot more time to work with, and black doesn't take much time at all. So a thread, one color here, that is fat, got to do a lot of things really quickly. And when it was done, it could then help out in areas that were much more complicated. And so that's why around the shadows, you see a lot of fine lines. That's work stealing. We're going to come back to this. But that's how to visualize it. Schedulers. You saw me do this earlier in code. I set minimum and maximum concurrency. Why would I do that? Why don't I just take the whole machine? Do all your algorithms scale? Sometimes the answer is no, right? That's actually kind of hard. So if you know your algorithm doesn't go beyond 8, set a max concurrency of 8. The other reason to do this is because I might want to force my work to run on a particular NUMA node, like you just saw. And so I'll show you that in code. Scheduler kind, again, you saw this in code. And what I've given you here is the top 4. There are actually a few more, but these are really the ones I expect you to use. You might sit there and say, look, I know how to debug threads, and looking at the UMS stuff makes me worried, or I just don't want to deal with that. I'm just going to go with thread scheduler. Maybe my tools don't work well with UMS threads. And that's true, by the way, that some of the tools do not work well with UMS threads today, some of the performance analysis tools. And so you can do your performance analysis by just setting the UMS, by setting the scheduler kind to thread scheduler. And you can, in fact, do this with one call by saying right in your main that you set the scheduler default to be a thread scheduler. And so it's a great thing to do, when debug or something like that. Or, I'm going to have this turned on if I would say a particular variable or something along those lines. And then I can now profile with threads scheduler. And now when I go production, I'm going to use UMS threads, because my tools are catching up with this technology. Context priority and the context stack size, you know these from threads, right? So it's the thread priority, it's the thread stack size that you use for your task. So these are things I expect you to think about when creating schedulers. Now, I talked about creating multiple schedulers. Why would I do that? By default, you get minimum of 1 and a maximum of the number of hardware threads available on that machine. This is a 4-core machine, and it's not hyper-threaded, so you have 4 real cores. Or it's a 2-core machine, and it is hyper-threaded, whichever way you want to look at it. So my default scheduler says minimum 1 and maximum 4. I create another scheduler, and I don't say what I want. So it'll take the default, which is 1 and 4. And what is the dynamic resource manager going to do? It's going to say, well, hey, he said he only needed 1 as a minimum. I don't have 4 now. I have both these guys asking from 1 to 4. I'm going to be fair. I'm going to give each of them 2. And it's going to try to start taking threads away and moving them around. So if you start looking in your profiler and you say, hey, but it's not perfect, well, that's because it takes time to stabilize that out. What happens if I now do, I get an idle core? Well, so the resource manager is told that core, there's no tasks running on it. It also is doing statistical analysis on regular intervals, paying attention to how deep your task queues are in the schedulers. So it sees that core went idle in those schedulers. And so it then says to, in this case, the other task, hey, the other scheduler, hey, you can have more threads. I'm going to give you this other core to schedule on because you've got work to do and this other guy does not. And that's part of dynamic resource management. But I will warn you, don't rely on this to do audio work, because it's at a fairly coarse grain. Okay, this is for coarse grain, long-running tasks. Now I define a third one. This one I said, look, I have to have at least 2. And it says, well, okay, you have to have 2. The other guys need 1. Fine. I can give you 2, and I leave 1 for the other 2 guys. And if I defined a fourth that now said I need to oversubscribe, that's what will happen, right? So if you have another one here, it's going to say, the resource manager is going to say, well, I tried my best, and now I'm going to oversubscribe. So you probably don't want to create 20 schedulers, but you do want to create enough to be able to express the quality of service that you expect for the tasks that are running in those schedulers. So let's go back to that ray tracer. And in this case, I'm going to add a number of them. Since I have 8 physical NUMA nodes on this machine, I've added 8 of these. And you're seeing all those. Well, I'm going to have to pause and unpause. There we go. And make them all run. And you're seeing the threads. Now let's see what it is from a core point of view. And yes, we're pegging the machine. I segmented this work, which is, embarrassingly parallel, 1 per core, and I'm very efficient. And I'm pegging that 48-way machine. And I'm going to calm it down. And if I go back to the laptop and I sit there and I take a look at the ray tracer code, there's my breakpoints. Not breakpoints, I want to see my, great. What is it? Control K. Bookmarks. We take a look at the code that actually does this. What it's doing is it's finding out how many cores per node by using 2 calls that we provide in the concurrency runtime, get processor count, get processor node count, doing a simple division, and using that to define the schedulers. Very simple. It's a demo, so I forced it to do that. But it shows you that you have the ability to control, in a very dynamic way, how your program runs on any architecture. You can sense what's going on with that architecture, and you can just run it. I'm going to come back here and take a look to see. OK, it's just calming down. I want these fans to spin down. Lastly, I'm going to talk about what else we provide. And I actually could go into further detail in some other demos, a little ad hoc after this if we want. But I want to point out that the world's changing. The last PDC, there was a Cray. I want to say it had 96 nodes. It was like this big. It's huge. This is 48, right? These are 6-core chips. Next year, we're getting 12-core chips from AMD. I think Intel has the same cycle. Actually, they might have some Xeons that are real high core count now. This is a 6U, so next year, it's going to be 96 cores in a 6U. Easy. Probably by the next PDC, it might even be half this size. So 64 as a limit is too small. 32, oh, we're gone, right? You can't use 32-bit programs anymore. You won't be able to use this machine, right? If I compiled for 32-bit, I can only get 32 cores on this machine. So I have to have a 64-core app, 64-bit app, so I can run on this machine. And I don't want to sit there and worry about the 256-core machine, which Pedro is going to show run, it's titanium, in this next hour. I don't need to worry about how I'm going to write code and test it. I mean, I have a hard time working in Microsoft getting access to a 256 core machine. Right? This is not something that you just have in every lab. Now, maybe we will in 5 years. But we don't today. And who writes code that lasts only a year? 2 years? 5 years? I'm not getting any hands. There's one person that has code that only lasts 5 years, 10 years. Now we're getting hands, right? 10 years ago, think about that architecture. It was a single core, and it was going really slowly. Today, we're writing code that is going to be used 10 years from now. Do you need to sit there and figure out what the hardware architecture is and then make the correct choices? Do you think you can? Who thinks they can? And the guys from Intel, you can't raise your hand, right? OK. The reason you need a runtime is to provide you an abstraction so that you can run on a 128-core machine. This is ConcRT running on a 128-core machine. It's a weird one, but we're running on a 128-core machine. We've run on 256-core machines. We've tested that environment. We've done that for you so that you can write your code once and have it run anywhere. There's been a lot of talks at PDC about parallelism. There's a couple more today. I do recommend that you watch Pedro's talk, which is covering all the new work that's been done on Windows Server 2008 R2 and Windows 7. That's next hour. There's some talks on Axum that's going on later. This is our kind of map that covers all those different areas. We're at SVR 10. And this is the list of what all those numbers mean. If you haven't gotten to see a lot of these, they are going to be recorded, so you can see them online. And I do recommend trying to capture that and trying to take some time and watch those. If you're going to be doing parallel code, learn from these videos. Look at the white papers. We're at www.msdn.com/concurrency. That'll be our portal to all the parallel programming coming from Microsoft. And there's multiple blogs that are feeding those pages, and we'll be posting white papers. The documentation in Beta 2 is very good for ConcRT. It's going to get better for RTM, but it's very good today. So do look at that. Do expect to actually be able to read that. There are some nice walkthroughs that you can do. I do recommend doing that. And they want us to have some feedback. I have actually scheduled us to have time for questions, and we have time for questions. I also have ad hoc demos that I could do if you don't have any questions. So we have a question down here.
Yeah, I'm just wondering, you talked about how you can do some intelligent scheduling with regard to things like human nodes. I was wondering, like on Intel's hyper-threading chips, can you do intelligent scheduling there? Like, say, you probably don't want to do two similar tasks on two virtual cores or on the same core because...
Well, we don't have, we as a runtime don't have the hyper-threaded information that we can work on. But that is a common request, and we're going to try to work with the OS people going forward. But today, I don't have that control.
So it just looks like regular cores to you?
To us, the hyper-threads look like regular cores. And I will say the Nehalem chips are really good about that from a hyper-threading perspective. We've seen significant improvements in hyper-threading on the Nehalem architecture. So maybe by the time we figure out how to provide that, it might not be relevant.
Curious, are you cooperative with the core parking stuff? I'm hearing about 2008 R2. So for power management, you've got to try and move processes or threads on active.
Right. So the real question.
It's almost the opposite.
Right. So the power management.
Can you repeat the question, please?
Sure. So the question is, do we cooperate with the power management sides of Windows, which is trying to, at this point, start moving threads around so that you can potentially run down cores. Best for the laptop scenarios. Thankfully, I'm in a server world. But that is actually a future goal. That is not in version 1. We don't work with the power control. Yes?
Does the dynamic resource management work across multiple processes or using ConcRT?
No, it does not work across multiple processes at this time. The multiple process, we're looking at that as a problem for the future. It's actually kind of a hard problem. So if you have some really good, clear examples, we'd love to have them for testing, because one of the hardest problems is figuring out who to not give all those cores to. Right now, we rely on the operating system, which handles it fairly. And that's fine. What ConcRT does isn't fair, right? You're actually saying, give this more priority than that. When I have 2 processors, how do I handle that kind of dichotomy of priorities? Do they have the same priority? Are they saying the same thing to each other? And so that's going to be something that we need to solve going forward. I've heard that as a request, and it is an active area that we've been looking at. But when we get into it, we realize it's a hard problem. OK, so more questions? Perfect. Yes?
Are there any issues with running this modern architecture on an XP or Vista machine?
Running this on, is there any issues running this on a Vista or XP machine? And the answer is no. We've tested on all those platforms. We go from XP all the way through Windows Server 2008 R2. What you lose when you go down level is that the operating system doesn't give us as much information about the architecture as I go backwards. Okay? And so we do as well as we can given what the operating system provides. And that is actually the plus aspect, right? So if you were writing to XP, you couldn't take advantage of what is in Windows 7. And so we're saying, go ahead, write for XP, and we'll take care of making the right decision for Windows 7 and Windows 8 and Windows whatever, right, going forward. So that's the idea. So I think you were first.
Having OpenMP up to now, and how easy it is, especially for a hard problem like ray tracing, that can come with parallel, rather than parallel form.
Yeah.
And using dynamic schedule to make it dynamic, would it make sense to use OpenMP and use the routers below OpenMP to make the schedule on user scheduling instead of on the threads?
Well, so Intel's OpenMP is porting to us. So his question is, using OpenMP, wouldn't it just make sense to put OpenMP on our runtime? And I say, well, yes, Intel thinks that does make sense. OpenMP is a very C-like environment, bluntly. And we're much more focused on C++. And OpenMP is really, really good for certain technical computing problems, which are nicely structured. But I can show you that ray tracer, and we did something nasty to it. We made it recursively, we cut a couple of different parallel calls, and all of a sudden I have 500 threads. And that's one of the things OpenMP can do to you as well, especially when you're composing different things. So you have your OpenMP application, and you call a math library that also uses OpenMP. And now all of a sudden you have an explosion of threads, which is fine until you get to a high core count machine and you discover your stacks overflow. So the concurrency runtime will help OpenMP there a little bit. Being able to provide more hints as to how you want to structure your application that you get with schedulers and schedule groups and task groups that you don't have in OpenMP. might actually make it run better. But that doesn't say anything negative about OpenMP. I think it's got a really good, it's a really good solution for that C Fortran market. And when it's running on the runtime, I think it's going to solve a lot of those problems. That's why Intel actually said, great, can we use it? Because they knew they needed to solve those problems. And in fact, if some of the folks are here from Intel, if you had any further questions about OpenMP from Intel. So James is up here in the front, so afterwards you can have some talks with them as well. And yes?
Are there any concerns with mixing concert and just native threads? Because the application that I work on primarily is a network service, where we'll have client requests coming in over TCP sockets and an I/O completion port.
Right.
And then would we be able to use concert to then parallelize the individual client requests themselves?
Yeah, and I think the answer is yes, they can coexist. Yes, they can work together well. You won't get some things like the ability to affinitize easily. On the other hand, your calling thread, it's going to try to affinitize to that calling thread if it's on the same thread. So you'll get some benefits. You have to be careful not to, let's say, have a parallel 4 that is calling into one of your routines that's spawning off 5 threads. Of course, the thread pool will help you there. We expect them to work together. Having a lot of threads isn't really horrible so long as you're not overflowing your stack. And that's what you'll see is maybe that you have a lot more threads created and oversubscription. But if those threads aren't doing any work, that's not really oversubscription, right? So they just sit idle while you're doing your parallel work. And so that's OK. I don't expect the whole world to go to concert tomorrow, and you can't make your whole app go to concert. So we will make them work. We do make them work well together, and I think we'll make them work even better going forward as there's more integration with the operating system. And that's things that we're talking to today. So if you have specific problems, I want to hear about them. This is the time to actually get into our next planning efforts. So if you have some problems, I'd like to hear about it. But today, on our applications that we're using and we're writing, we don't see any problems, significant problems. But you have to be careful. Other questions? Yes?
Speaking to the multiple process support, if you have multiple processes that are going to be running at the same time using concert, how do you envision tuning them? Or, I mean, do you have to take into account?
So there's 2 parts to your question. How do I tune concert applications? That's one problem. How do I tune multiple concert applications that work together? The first one is that there are a lot of really good tools in Visual Studio 2010. There's a parallel, I want to call it parallel analysis tool. I forget what it's called today because they've changed the name. I usually call it parallel performance analyzer. But if you can do some really nice parallel analysis. Rick showed that on Tuesday. I don't know if you were at that talk. Actually using that analyzer and being able to see, there's 3 different views. You can actually see the whole CPU view, and you can see how you're using your CPU from your application perspective, from that one application perspective, and you can see the system and how other applications are taking away from your application's use of those cores. You can see kind of the swim lane view of how your cores are being used, and you can also see if you've got a lot of things flipping between cores, which hopefully you will never see from concert. When you have more than one of those, you can analyze each one of them separately. You'll be saying, well, how are these running on my system together? And now that my question comes to you is, how much control do you have on your systems? If they're a standalone server that you're being able to define clearly, then now you start going to schedulers and saying, hey, I want to limit this process to only using half of my box. And I want this other process to use the other half of my box. And try to divide it that way. If you don't have as much control, then it's going to be a little bit more challenging. And it's the area where we start talking about how do I do cross-process resource management on CPUs. And that's an area that I think, that's a problem I want to have. Because today I don't have that problem. Today, my applications are single-threaded. So I'm going to say to you that when you start having that problem, you've gotten to a point where you're having success. You've paralyzed your applications to the point where they're using all your resources, and now you're worrying about your applications conflicting, not how do I make my applications scale. So when you get to that point, I hope to have tools to solve it. We're not there yet. So if you have that problem, I'd love to hear about it. Yes?
You showed a demo where you compare inserting two events versus the concert event. I'm just curious, for the concert event, is that something you use across process boundaries?
Not across process boundaries. Concert is within the single process. So he was asking, can I use those events across process boundaries, and the answer is no. Do another question?
So our application is targeted for 32-bit platforms executing on 64-bit OS devices.
Yeah.
Do I get any UMS support at all in that case?
So the question here is, I have a 32-bit app. That's what I deliver to my customers. Do I get any benefit from UMS on 64-bit? And the answer is no. You'll just get your threads. And when I do that demo, I often actually recompile it. You know, let me run it in 32. Let me run it in 64. And you see it that way. I was just reducing our time overhead. Did I see another question in the back? No? OK. We are literally out of time. This is probably the first session I've been at that actually stayed in time. I did try. I will be around. I'm going to stick around and actually go to Pedro's talk next. And so I'll be here, and then I'm going to go over there. And then I'll probably be down at the booth until noon today. My email is dgroff@microsoft.com or dana.groff@microsoft.com. If you want to ask questions or you have specific things that you think we should be doing in addition to what we've delivered in 2010, I'd like to hear about it. If you have specific problems that you're running into that the concurrency runtime does not address, I want to hear about it. This is the time to actually get into our planning process. They want you to give feedback. I haven't actually checked these out, but they are giving donations to charities for everybody who fills out feedback forms. So do it. There's a lot more on Channel 9, and there probably will continue to be more. I'm actually planning some Channel 9 sessions after PDC that'll be doing some easy walkthroughs. And there'll be some white papers coming out over the next couple of months on how to use Concert up through RTM. That's it for today. Thank you very much.